Today I will talk about variation of stresses along cross section of any material. Okay, so stress variation with cross section. So till now you have learned how to calculate stress and also how to calculate strain. Okay, so now let's learn if we have a case like this one. Okay, and let's say you are applying your tensile load like this. Okay, and if you take any normal plane here, let's say this is MN, you can calculate the stress in this normal plane, and that is your P tensile force divided by this cross section, okay, along this plane MN, and let's say that is your A. Okay, so you can easily calculate your stress. Now, as this heading suggests, what is the stress variation if we change this cross section? Okay, so for understanding that topic, let's consider we have a plane at an angle of theta. Okay, so this is the plane which is making an angle of theta with this normal plane, that is MN. Okay, and this angle is theta. So this is theta. Okay, so to discuss all about the stresses in this oblique plane marked in yellow color, what we have to do, simply we have to separate this left out portion. Okay, we will separate this left out portion. So the free body diagram looks like this one. Okay, this is the load applied P, and our plane is this one. The yellow color is our plane. Okay, so the very first thing we have to find out the resultant force, internal force due to this external force P. Of course, that is also P. Okay, from equilibrium equation, if you simply put this equation, summation of Fx is equal to 0, you will get the internal force acting here is P. Sorry. Okay, now if we resolve this P in two parts, first one is, let's say this is the normal to this plane, and second one is tangential to this plane. Okay, so this is tangential to this plane. It has two components. Okay, and now here you can see this angle is theta. Okay, so definitely this one is also theta. Clear? So what is the normal component of P? Of course, this is coming as P times cos theta. Okay, and what is the tangential component? Of course, this is P times sine theta. Okay, so now what is the cross sectional area now? This yellow color. What is this area? The area is now, simply initially assume the area was in this Mn, it was A. So now it is simply your A divided by cos theta. Okay, so you have all the parameters. Now if I ask you what is the normal stress acting on this yellow plane, that is this one. What is this normal stress? Simply the normal stress, that is sigma n, this is normal force, that is P times cos theta, divided by the area, that is A by cos theta. Okay, and it will give you this one, that is P by A times cos square theta. Okay, and you know that P by A is nothing but the original normal stress, that is sigma. Okay, so we can rewrite this one as sigma times cos square theta. Any issues? Okay, now if I ask you what is the tangential stress or the shear stress, simply that is tau, the tangential stress acting on this plane, oblique plane, is the force, that is P sine theta. Here this is force, and the area remains same, that is A by cos theta, which gives you again P by A. Okay, again P by A times sine theta cos theta, or you can rewrite as half times, this is half times P by A is what? Yes, sigma or stress in the normal plane, this one, times sine theta cos theta, and sine theta cos theta has been converted into half times sine 2 theta. Okay, so now you have got the equation of normal stress as well as the shear stress in this oblique plane. Okay, now let's analyze this two equation. So first one is normal stress. Okay, so from this equation, what we can say, that sigma n, okay, sigma n is a function of cos square theta. That means when theta is equal to 0, your sigma n is equal to sigma, and here when sigma theta becomes 0, of course the plane becomes mn, and that's why sigma is equal to P by A. So it is validated. Okay, and again, what about shear stress? Here shear stress is a function of sine 2 theta. That means if sine 2 theta is equal to 1, in that case tau is your maximum. Okay, that means if this theta is equals with pi by 4 or 45 degree, we will get tau as tau max. So here if theta becomes 45 degree, there the shear stress is maximum. Okay, so it has a very big implication. If any material that is weak in shear strength compared to its tensile strength, definitely the failure will be along the 45 degree of its axis. For example, if we simply take a wooden post like this, okay, this is a brittle material, and if you apply a huge compressive load like this one, okay, do you know the failure plane? Yes, here shear strength is weaker than tensile strength, that's why the failure will be like this. This is the failure plane, you can check it yourself. Okay, so this was the implication of these two equation. Now what will happen if I take another section at a distance of angular distance of 90 degree plus theta? That means let's rotate this yellow section with 90°. Okay, and now the yellow section becomes this one. Agree? What we have done, we have simply rotated the previous yellow section with 90°. Okay, so now if I ask you what is the normal stress here, as well as what is the shear stress here. Okay, what is the shear stress here? So what you have to do, you have to simply redraw this one. Okay, this was our material. Here is the tensile load P, here is the tensile load P, and initially the normal section was this one, that is Mn, and here the normal stress sigma was simply P by A. Okay, and it was P by A. Okay, so let me use some different color. Sigma was P by A, and now what we have done, we have taken our section like this. This is the plane with angle of, the angle is 90° plus theta. This is the angle, 90° plus theta. Okay, so simply take out again the left portion. Okay, take out the left portion of this section to analyze the stress, and the free body diagram again looks like this one. Okay, the external load is applied here. This is the section, this is the plane under consideration. So first step is we have to find out again the resultant internal force, that is P. Okay, and again just take the component here. Okay, so now the normal component is this one. This is the normal component. Okay, and this is the tangential component. Okay, so here which one is theta? Yes, this angle is theta. This is theta. So the normal component is P cos theta. Okay, and here it is the tangential component is P sin theta. Okay, so now you can easily calculate what is sigma n. Okay, so sigma n you can calculate as per this formula, and as well as the tau n. Simply put the cross-sectional area underneath these forces. Okay, but here I will manage it in some other ways. What I will do, I will simply put theta is equal to theta plus 90° in this equation. Okay, so for sigma n I will simply put this equation here, that is sigma times cos square. Instead of theta I will write it as 90 plus theta, and it will give me sigma, and here let's say this is sigma n dashed. Okay, so sigma times sine square theta and tau a dashed. Okay, so tau dashed is coming as again half times sigma times sine 2 theta. Instead of 2 theta I will write it as 180° plus theta, and it gives us minus half times sigma times sine 2 theta. Okay, so what is the implication here? Here you can see that any mutually perpendicular to plane, in this case this one, okay, these two plane. Here you can see that this sigma n plus sigma n dashed is equals with sigma. Why? Because cos square theta plus sin square theta is equal to 1. So we can rewrite it as that sigma n plus sigma n dashed is equal to sigma. And this is valid when these two planes are mutually perpendicular. Not only that, in these two mutually perpendicular plane, the shear stress tau, these are identical but opposite in nature. Here is the minus sign. Okay, clear? So this is all about today's lesson. And just one more addition: when this shear stress is negative and when this is positive, simply to understand that if you take any section, let's say this one, and if here the stress act like this, it creates a clockwise rotation about the center, and this is positive. Okay, and if you take an element like this, okay, and here shear stress act like this one, okay, and here you can see that about this center it creates an anti-clockwise rotation, and this is negative. This is the sign convention. Okay, so that's all for today's lesson. We will meet again with another lesson next day.